Hello everyone, welcome again. So today's lesson will be on metals in Year 11 Chemistry. And in today's lesson we're going to focus on empirical and molecular formulae. Okay, so we're going to look at what an empirical formulae is and what a molecular formula is. So here we have something that's like an ionic compound, and we'll see how ionic compounds are dealt with empirical formulae. And here we have something that's more like a covalent molecule, and we'll see how this is dealt with molecular formulae. Okay, so this is what we're going to cover in today's lesson. So firstly, we have to talk about the importance of chemical formulae in the first place. So why do we need them? Well, chemical formulae are important because they're a standardized way of communication between chemists. So if, for instance, I was to draw a chemical and give it to another chemist, then they would know instantly what I'm talking about, or at least they should understand what this chemical is made out of and what it possibly looks like even. Okay? So they're important for chemists because we need to be able to talk to one another, particularly if we found a new chemical, or we think we found a new chemical, or some new application for a chemical. We want to be able to show people what it looks like and tell them what it is. So that's the way that we communicate, by using these formulae. So in general, there are two types. There's the molecular formulae, which sort of looks something like this. Okay. So this one is what we call a molecular formula. Actually, this is even, within molecular formula, there are structural formulas, which is this thing. You can actually see the structure of the chemical, but we won't talk too much about structural formulas in today's lesson. And the other one is empirical formulas. And empirical formulas a lot of people don't use them as frequently, or they don't think about them as much, but they are actually very important for naming ionic compounds and also naming covalent network compounds as well. Okay. So, molecular formula. Okay, so what is it? So a molecular formula shows all the components of a compound. Okay, so here we have the molecular formula, and here is the structural formula of the same chemical. They're both the same. This is acetic acid or vinegar. Okay, so these are the same thing, and you can see that they show every single part of the chemical. You can see there's 2 carbons, there's 2 oxygens, there's 1, 2, 3, 4. There's 4 of the hydrogens. So you can see that in the molecular formula, we can see all of the different components. In a slightly more condensed form, you can still see 2 carbons, 2 oxygens, but we have H3 and H rather than having this singular H structure. Okay. So within a molecular formula, all of the elements and the number of atoms of that element are present. Okay, so what I mean by that is you can see that you can see all the carbons, you can see all the oxygens, and you can see all the hydrogens, and how many of each one there are, okay, in a molecular formula. So you can see there are 2 carbons, there are 2 oxygens, and there are 4 hydrogens, right? So the molecular formula tells you what's in the actual compound and how many of each type of atom or each element are in the compound as well. So for instance, ethylene, which is something that you'll study ad nauseum in Year 12, has 2 carbon atoms and 4 hydrogen atoms. So the molecular formula is C2H4. Okay, so that's the molecular formula of ethylene, C2H4. And you can tell instantly that there are 2 carbons, and 4 hydrogens. Okay, so very simple what a molecular formula is. So this type of formula is typically used to represent covalent molecular substances. And that sort of makes sense because it's called a molecular formula, so it should probably name things that are molecular in form. Okay, so typically we'll use these molecular formula to represent covalent molecular substances. Okay. So what about an empirical formula? We've talked about these, we sort of mentioned them earlier. So what are they? Well, an empirical formula shows only the smallest ratio of the component elements, okay? So here we have, what we see is there's repeating units, okay? So here you can see that this unit repeats itself several times, like there's one there, and there's one there, and there's one here, and here. So you can see that this unit, this yellow-blue unit, repeats itself. So if we were to do this in the molecular formula way, we would have to keep writing yellow, blue, yellow, blue, yellow, blue, yellow, blue, or just, yellow times some stupidly huge number, times blue, then yellow, big number, blue, huge number. And so it would just be really confusing. So it's easier sometimes to just use the smallest ratio of elements, okay? So an example of this would be ethylene, okay? So ethylene has 2 carbon atoms and 4 hydrogen atoms. So for every 1 carbon atom, there are 2 hydrogen atoms. So the empirical formula would be just CH2, okay? So before we saw that it was, in the molecular formula, it was C2H4. But this one, because we're using the smallest ratio, it's just CH2, okay? And so you can't really tell much from this equation, or this formula. So the molecular formula is generally better for molecular substances. But for ionic substances and covalent network substances, this form is sort of the de facto standard, or it's the standard that we use. So typically this type of formula is used for covalent and ionic substances, okay? So that's what I just mentioned. And the reason is because if you have thousands upon billions of repeating units in one crystal, you might as well just say it's the smallest component or repeating unit, right? Because if I keep chopping up my crystal of, say, NaCl, let's say I had it. So here's my NaCl crystal. Okay, so there's my crystal. If I was to chop it up, say, down here. So I got rid of these guys. This would still behave chemically the same way as the big crystal did. So there's not any real advantage in naming Na3, because there were 6 total, so Na3Cl3, right? So the reason is that it just makes it easier to name, because crystals often have billions and billions of atoms, or ions. So if I was to try and write Na, say, times 10 to the power of 26, Cl 10 to the power of 26, that just becomes very cumbersome. It just looks very messy. Even though NaCl, just one Na, one Cl, behaves exactly the same way as a billion of them put together. So that's why we use these empirical formulae. Okay. So that concludes today's lesson on empirical and molecular formulae. We looked at what they are and how we apply them to different chemicals. So for molecular formulae, we tend to use them for molecular substances or covalent molecular substances. And for these empirical formulae, we use them for covalent network and ionic substances. So that's what we've studied today, and hopefully as we move on to the question segment, you'll see more about what the advantages and disadvantages of these methods are. So explain why molecular formulae are not used to represent ionic or covalent network substances. Okay, so I kind of broached on this moments before when I was talking about ionic substances. So molecular formulae are used in general to represent substances that exist as discrete molecules. So that's the first thing. They're not really designed to work with ionic substances. So ionic and covalent network substances both exist as large aggregates of repeating units. Okay, so the molecular formula is good for things that like to exist by themselves. So CO2 will just float around by itself. It doesn't want to interact with other CO2 molecules. But ionic and covalent network substances exist as very big chunks of lots of repeating things. So there'll be like NaCl here, followed by NaCl here, then it just keeps repeating, right? So it's very different in its structure to a covalent molecular substance. So it would be cumbersome to represent these types of substances with molecular formulae, since they exist as innumerable amounts of repeating units. So as I mentioned before, if I was to write it as a molecular formula, I'd have to write Na to the power 10 to the power of some huge number, Cl 10 to the power of the same huge number. So it just becomes very, very cumbersome and doesn't really tell us anything other than there's some very large number of Na and Cl ions in my crystal. So it's just because it's too cumbersome, that's why we don't use them in ionic or covalent network substances. Question 7. Carbon tetrachloride was a commonly used refrigerant. Write the molecular formula for this chemical. Okay, so we know the name, so what's its formula? So carbon we're going to look at first. So there's one carbon atom, and that's given the symbol C. Tetra is 4, so it's not quad in this case, it's tetra. That's how we denote 4 in chemistry. Okay, so it's 4. Chloride is Cl, as we know. Okay, so finally, so tetrachloride is Cl4 so tetrachloride is Cl4. So the final answer is CCl4. Okay, for you big chemistry buffs out there, this is also called tetrachloromethane. So it's also called tetrachloromethane rather than carbon tetrachloride. It's whatever you really want to say for this one. Okay, so that's how you do it, based on the name. The name tells you everything you need to know about the chemical. That's why you have the name and convention that we do. Okay, question 8. Describe one major problem associated with the use of empirical formulae for carbon compounds. Okay. So empirical formulae provide only the simplest ratio of elements in a chemical compound. Okay, so it just tells you what the simplest ratio is. It doesn't tell you anything about the structure. It doesn't tell you anything about the number of those chemicals in the solution, in the molecule. This can result in several compounds possessing the same empirical formula. Okay, so lots of different chemicals could have the same empirical formula, but different numbers of carbons, different numbers of hydrogens, different numbers of oxygens, all sorts of different things could be happening. But the empirical formula of all of those chemicals would still be the same, because it's just, remember, the simplest ratio. So one example is formaldehyde and acetic acid. Both have the same empirical formula, but they possess extremely different chemical characteristics. Okay, so this acetic acid is vinegar. We eat it, we put it on our chips, things like that, or in our salad or whatever. But formaldehyde is a carcinogenic chemical that helps preserve dead bodies. Okay, so you can see here, they obviously have very, very different chemical characteristics, but they have the same empirical formula. So if you can imagine, if we got them mixed up, so we put formaldehyde in our food and acetic acid to preserve our dead bodies, then that would be a disaster waiting to happen, okay? Because formaldehyde is toxic. So the only reason that we don't use empirical formula for carbon compounds is the ambiguity because a lot of carbon compounds can share the same empirical formula. Okay, and this is just one example of that. So what information about the chemical compound do you need to convert an empirical formula into a molecular formula? Okay, so if I have an empirical formula, can I actually turn that into a molecular formula? And if I can, what extra information do I need to do that? Okay, so all you need to know is the molecular mass of the compound, and then you can convert between the two different formula types. So as long as you know the molecular mass of the compound, then you can convert between the two. So question 10. A substance has an empirical formula of CH2. What is the molecular formula of this compound? If the molecular mass is 42 grams per mole. Okay, so we now have all of the information that we need to work out the molecular formula. So since an empirical formula is a ratio, the general formula for the compound would be CyH2y. Okay, so we know that there's always 2 hydrogens for every 1 carbon. So it means that whatever the number of carbons there is, there will always be 2 times as many hydrogens. So we can just put y there because we don't know yet how many carbons there are to start with. Okay. So we know that all of the component molecular masses add to equal 42. Okay, so the molecular mass of a single carbon atom times y carbon atoms plus the molecular mass of a hydrogen atom times 2y hydrogen atoms will give, add them all together, that will give us 42. So we get C times y, that's 12.01 times y plus 1.008 times 2y gives you 42. Okay, and there you have the equation. So then we know that if we do the maths, 14y equals 42. So y equals 3, and obviously 2y is 6. So if you write it in your general equation now, you get C3H6, which is propene. Okay, so that's how we work out these questions. So that concludes today's lesson on molecular and empirical formulae. We looked at what they are, what each of them is, and what are the advantages and disadvantages of using molecular formulae or empirical formulae in different cases. So in the next lesson, we'll be doing a first-hand investigation. So I hope to see you at our next lesson.